I'll check based on that, and I'll count the number of times they are paired, the number of times they pass the check, that's success, and I'll count the number of times they weren't paired, that's the number of times they failed this check, which is failure. And if you really did have that belief, there's probably a very high ratio of S to F. There should be lots of successes and few failures. And we can just use standard probabilities to compute a very crude approximation of what the probability is here, and we'll just rank the errors based on the strength of the underlying belief. Okay, so I'll just give one example, one slide, and then we'll go to the conclusion. So some of the worst errors you can get in a real system are use-factor-free errors, and the problem is in many real systems, these subsystem designers just go a little haywire and they design their own malloc and free implementations, and so you have no idea what all the free functions, that K-free frees things and K-malloc fails things, but you have no idea about foo and bar and whether they free things or not. And the problem is if you use classical compiler analysis on custom free and allocation functions, it's really hard to figure out what they are, because all they're going to look like, all alloc is going to look like is a linked list DQ routine, and all free is going to look like is a linked list NQ routine. It's not all clear that their contract is allocation and free. On the other hand, if you use belief analysis, it's pretty easy to behaviorally infer free functions. So what does a free function look like? Well, basically it's a pointer for sinks. It's a sink for pointers. So if you pass pointer P to foo, if foo is a free function, if it's not, you're not supposed to be using P afterwards. So every time, if we see lots and lots of calls to foo P and very few uses afterwards, we get more and more belief that you actually believe foo is a free function. So conceptually, the way this is going to work is we assume all functions free all their arguments. So in reality, use some filtration just for scalability reasons. And we're going to emit two error messages, two messages. So we'll emit a check message at every call site. So in this case, we have two functions, foo and bar. We'll assume both of them free their sole parameter. Every time we see a call to foo, we're going to emit a check message. This is basically the number of times you had an opportunity to screw things up. So here there's 3 calls to foo, there'll be 3 check messages. And then we'll also emit error messages every time an error actually did occur. So here, after every call to foo, the pointer of P gets dereferenced. So there's a call to foo, there's a dereference, call to foo, dereference, call to foo, dereference. So there's 3 checks, there's 3 errors. It's not looking too good. Bar is a bit better. Again, there's 3 checks, check messages. In 2 cases, they just overwrite P with 0. So there's no dereference, there's no use, this is fine. These are not errors. And in one case, they dereference it. So for bar, there's 3 checks and there's 1 error. Looks a bit better. So the way we're going to use this information is we're going to rank the errors using a statistical test, the z-test statistic, which is a trivial statistics 101 function, where we feed it the errors and the checks, and it tells us how probable something is, roughly how probable the belief is. So in our case, the z value for 3 checks and 3 errors is going to be fairly low because that's not convincing at all. You believe it's a free function. The z value for 3 checks and 1 error message for bar is a bit higher because it's a bit more compelling. So what's going to happen is we're going to rank bar's error messages first and then foo's. In reality, neither is very compelling. So what happens when we do this and you run this type of checker on Linux, immediately 23 new free errors pop out. And this sounds kind of not that interesting, except that this was after spending a couple of years groveling over Linux, aggressively trying to find every free function we could because we wanted to publish as many papers as possible, and that always helps if we have higher bug counts. So we spent a lot of time trying to find all these free functions ourselves. And then when we came up with this idea, I just ran it on Linux just to see what would happen. I didn't expect much to happen. And the fact that we found all these new free functions and all these free errors was we were a little nonplussed. And you typically don't spend as much effort as we did trying to customize or figure out what your system does at this level. Okay. So I guess I think it's getting a bit late, so I'll go ahead and summarize. So 2 high bits. You can make a compiler aggressively system specific, and if you run it over the code, checking for system specific rules, you'll find lots of bugs. And the goal here is we want to make it so that we want to make the compiler optimized so that every time you have a rule You look in your documentation, you see sentences that say never or always. If you do A, you better do B, and are in context X, never do Y. You want to make it so you can encode those in terms of compiler extensions and then force them in a hard way. And the good thing about this is that you can, now instead of everyone having to obey the rule, knowing all rules and obeying all rules all the time, you just have one person sit down, digest the rule, write a checker, and impose it on all code. This is actually really nice and fast. The other heading is that you can actually infer a lot of checking information directly from the source code without anyone holding your hand, by just looking at the program and trying to figure out what the program seems to believe is correct and then checking these for contradictions. And anytime you can find errors without knowing what the truth is, this is a really good thing. The experience for the past 7 years or so is anytime you take a checking approach like this and you apply to code that's never been checked, you always find lots of bugs. If you don't, you immediately go and you look and you try to figure out how you misconfigured the tool, because there's no possible way there could be no serious bugs. And that's true for our approach and also for other people's approaches. Static checking just seems to work pretty well. Okay, so I guess we can turn this over to questions, both for Ben or for me. Just quickly, if you want to test Comparity, the way they have it set up now is you just do a free trial. You can just contact Ben or sign up for a trial. And the way this works is they come out, they send a sales engineer and maybe a sales guy. They come out in the morning, you run it over the source code, they find the bugs, and then they show the bugs in the afternoon or the next day, whatever's convenient. And then you can actually see what the real bugs are that the thing found, and whether you like the bugs or you think they're important or whether they're not that interesting. And so there's NDAs in place, and no one's exposed to anything. As you see, we don't talk about the bugs we find. And you can just see exactly how it works on your system, what it's worth it. There's also other ways you can do lunch and learns. And I think Ben can go on about this as much as necessary. Okay. Okay, so I guess I can start with different questions. So on average, how many extensions to Comparity customers write per customer code base? So typically, out of the box, you do nothing. There's already a suite of checkers, and we already understand, the Windows interface, the Unix interface, the C library interface. There's already checkers customized for these things. So, within the first warning, with basically the only parameterization that has to be done is saying which compiler you use and which build environment, you can immediately find errors. So we try to do this so you don't have to do any setup whatsoever, and you can already find errors. And then over time, if you want to do more and more, if you have weirdo rules that only your system has, you can actually add these in. But we definitely try to make it so that the value of the tool gets demonstrated up front, so you don't waste a lot of time doing something that's useless. And there's some companies that have spent actually a lot of time making their stuff aggressively system specific. And there's others that just take it out of the box and use it and they fix those bugs. Okay. Do we have access to the source for your pre-built checkers to use as examples? Yeah, there's actually tutorials that can be set up. There's guys that come out and give help you with the running. There's also a bunch of samples, and there's the usual web-based tutorial stuff. So we try to make it so other people can write things pretty easily, because that makes the tool more useful, which makes them more likely to buy it. All right. Have you done any research into objects as opposed to source analysis? I haven't really done much of that. I typically check like operating systems and stuff. There has been a lot of work on that, and actually we've hired people who have done that work, like Scott McPeak, who's very, very sharp. So personally, I haven't done much object analysis. As a company, there's people who do that type of stuff. Okay. Where is this presentation? Slides can be reviewed. They should be off my webpage. If you just go to do a Google on Dolphin Angler, this is probably one of the first talks that's on there. And if not, you can send me email. Like you can also send Ben email or Kathleen email. Anyone who's affiliated with this webinar, I think you can send an email to, and they'll send you the presentation. Do we have checkers that already check embedded systems? CX works. I believe so.